All right, we got two problems here. Let's go ahead and get through these. So, what do we got here? For problem one, here we have this square-shaped triangle, this triangle-shaped plate submerged in water. Right? So it's kind of hard to, I couldn't make a picture for this easily. But the picture that's going on here is we have a triangle shaped like this. Actually, let me use a different color. Let's use purple seems good. Let's say we have a triangle, it's shaped like this. Let's say the surface of the, no, please turn blue. The surface of the water is up here, right? The dimensions here, this part from here to here, this is going to be 3 meters, sorry. This triangle is 9 meters tall and 6 meters wide. Okay. So for something like this, the easiest thing to do, right? So we have to figure out a couple things here, right? We have to figure out this depth function, right? Depth. And we have to figure out the length function. Right? And then we can start setting up our integral here. Okay? So, what do we need to do then? We need to choose a coordinate axis. A set of coordinate axes. So the way we're going to do that is we're going to put the y-axis right along this edge of the triangle here. Right? Since this shape doesn't have any symmetries that we can exploit here, we don't want to put it right down the middle this time, like we did in the lecture videos. This one we want to put right along the edge here, right? And then in this case, we're going to put the x-axis right here, right? So then, this corner right here is at the point 0, -3. This point right here is at the point 6, -12, right? Because this is going to be, the bottom of this triangle is going to be -12, or 12 feet, or 12 meters deep, sorry. Okay. So using this information, we can get an equation for this edge of the triangle, right? So let's see, we'll use y minus -3 equals, will be -12 minus -3 over 6 minus 0. So that's going to be -9 over 6, or -3/2. Oh, sorry, I forgot like a whole bunch of stuff there. Okay. This is going to be times x minus 6. So that's, we already said is that's -3/2 x minus 6. Right. So if we here want to solve for x, right? So on this side, this is going to be y plus 3. So what we want to do is first off multiply both sides by -2/3. If -2/3 y minus 2 is x minus 6. And so x will be equal to -2/3 y plus 4. Okay? Is that right? That looks good. Great. Yep, excellent. Right, let's see, the y-intercept should be 3. Good. I think I did that right. Okay. Right, -12 minus -3, 6 0. Oh, sorry. I mixed up my points. This is supposed to be 0 here. I used that one. So there's nothing there. So actually it's just... Okay. Sorry, I forgot what was going on there. I mixed up my points. All right. So the reason we want that is because this ends up being our length function. Is if we measure from here to here, this length is just x. Right? So in other words, L of y, our length function, is simply going to be minus 2/3 y minus 2. Right, now we need to get the depth function. Right, so the depth function, if we pick any depth here, y, right, it's going to be the depth that this is going to be under is simply minus y. Right, so h of y, the depth, this is just minus y again with the coordinates we have set up. Right, so if we put the x-axis at the top of the water, the depth function is actually always going to be minus y, which is quite nice. Right, so here this is length, and this is depth. Okay, so then the total force is going to be the integral. Remember, it's weight density times length times height. So the weight density in this problem is 9,800, right? Times the length, which is minus 2/3. Whoa, I cannot write today. 2/3 y minus 2 times minus y, dy. All right, and then we need to set up the bounds. Remember, the bounds here are going to go from the bottom of this shape to the top of it. This is -12 down here, -3 up here. We integrate from -12 to -3. Right? And again, this isn't a particularly interesting computation, so I'm just going to pop up Mathematica to compute this real quick. So we want to integrate 9,800 times minus 2/3 y minus 2 times minus y. Right, we want to integrate that where y goes from -12 to -3. And this is going to be equal to 2,381,400 newtons. Right, this force is in newtons here. And that's that. So for a relatively simple shape, we get something like this. Now it gets a little more interesting if we want to do something that's not a simple shape like this. Or, well, I shouldn't say that. But if we have a shape that's maybe a little bit harder to describe. So that's where problem 2 comes in. Right? Now the interesting thing about, these problems is we sort of get to choose where to put our coordinate axes. That's the most important part here. Because we can always adjust, what the depth function has to look like, what the length function has to look like. But choosing your coordinate axes in a wise way will allow you to, potentially, exploit certain features of your shape. All right, so let's see what that looks like here. So here, in this one, we imagine having a circular porthole on a submarine. So that's like, a window on a submarine, right? It's going to be in the shape of a circle, right? This circle here, this porthole, right, is meant to have a diameter of 1 foot. So maybe let's use this gold color here. this is going to be 1 foot across. Okay. And the center of this circle is 15 feet under the depth of, or underwater. Okay. So this depth right here, see, what color did I use for that here? Orange. Use that same orange. From this here to the top of the water, this is going to be 15 feet. All right? So given this information, how do we find the force exerted on this window? Right? So this one, seems like we have less information, but it's actually fine. We're good to go here. Right? So how do we exploit this situation? So actually, let me get rid of the 1 foot here. And let's just say that, let's write this over here. The diameter is 1 foot. Okay. So what I'm going to do is say, okay, this is the center of the circle right here. I'm going to put the origin of my coordinates right here. Right, so this is the y-axis. I want this right here to be the x-axis. Now you might ask, well, why do I do something like that? Well, if I don't do that, the equation for this circle is actually quite a bit trickier. But if I make the center of my coordinates right here, the equation for the circle becomes quite easy, right? This is now a circle with center the origin, radius 1/2. So this is x squared plus y squared equals 1/4. Right? All right, so again, here's the length function, right? Our length is this x variable here. We can do that trick that we did in the lecture videos. Since this side is symmetric to this side, we can find the force over here and then double it. Right? So, or we can find the length here, I should say, and then double that. That's equivalent to finding the force on this side and then doubling it. Right? So, to do that, then, we need to solve for x here. All right, so if we solve for x, we're going to get square root of 1/4 minus y squared. All right, so we're taking the right half of this. So then the length, length, this is L of y. This is going to be twice this number right here. All right, look good, hopefully. All right, now the question is, how do we find the depth function? Well, we need to find the distance from any point here to this point up here, right? Any y value up to here. Oops, what are you doing? All right, so actually that's not too difficult to do, right? Whatever the y value is here, if we do 15 minus y, that gives us the distance from the top here to whatever our y value is. So like, for example, if we chose, let's erase this one here. God, I'm running out of colors. Let's say we choose this depth right here. Then the distance from here down to here, this is going to be 15 minus y. Right? So if y is negative, we add a certain amount to 15. If y is positive, we subtract a certain amount from 15. Right? So the height, or I shouldn't say height, but depth, h of y, is going to just be equal to 15 minus y. Right, so that gives us the length of the window at every height is just twice this. The depth is this. Now we just do the usual. Right? So the total force exerted on this is going to be the integral of let's see, we need the weight density, which is 64, right? Yep, 64 pounds per cubic foot. Good. Times the depth, so times 15 minus y, times the length, which is 2 square root of 1/4 minus y squared, dy. Right? And then what are the bounds on y in this case? Well, we just go from the bottom to the top, right? Well, this is a circle of radius 1/2, so the bottom is minus 1/2, because that's how far we go down. The top is positive 1/2, because that's how far we go up, right? So this integral will give us the total force on this. Now, this integral here, right, so I'm going to take the 64 and this 2, multiply them together and get 128. Computing this integral is a bit interesting, right? So I'm going to multiply the 15 minus y times this, and then I'm going to split it into 2 parts, right? So here, we'll get 15 integral from minus 1/2 to 1/2 of square root 1/4 minus y squared dy. Okay. Oops, that wasn't supposed to be there. And then minus y times the integral from minus 1/2 to 1/2. Oops, that y is not supposed to be on the outside. Y square root 1/4 minus y squared dy. Right? So, now of course we could toss this into Mathematica, but I really want to do this one by hand to kind of show off some techniques we can use to compute these. So, all right, we're kind of stuck with this 128 here. 15. Now, look at what this integral is. This is something that you should be able to interpret. This here is the area of the semicircle of radius 1/2, right? So this here, right, again, if you think of how you set up the integral for the area of a semicircle, it's going to look like this. All right, so the area of a semicircle is pi r squared over 2. So this is pi 1/2 squared over 2. Right? This integral here, this is an odd function. Since that's an odd function, that integral is 0. Pretty good, huh? All right. So now it's just a matter of, all right, well, let's start simplifying this. This is 128 times 15 times pi over 8. And let's see, this will simplify a little bit. 128 is actually a power of 2. Let's see, so 128 over 8 is 16. So we want to do 16 times 15. So this is going to be simply 240 pi pounds of force. Right, so that's, approximately, let's see, where's my pi key? There it is. This is approximately 753, let's just say 754 pounds of force. Right. So these physical problems here like this, as, with actually many physical problems, they can be made a lot easier if you choose your coordinates in a meaningful way, right? In a convenient way, right? Put the origin somewhere that makes sense. So like in this first problem here, it makes a lot of sense to put the y-axis along the left edge, the flat edge of this, and put the x-axis at water level. Right? Putting the x-axis at water level will guarantee that the depth function is really simple. On the other hand, doing that here, while the depth function would still be negative y, On the other hand, the length function would get a little more complicated, right? Instead of just simply the length function being 2 times square root 1/4 minus y squared, instead we'd have something like 2 times square root of 1/4 minus y minus 15 squared. Right? A little more complicated there. So it's better to avoid that kind of complication if we can. And we easily can by saying, we have a circle. Circles are really great if their center is the origin, so we'll put our coordinate axes at the origin. Right? So the depth function becomes a little more complicated, right? But not very complicated at all in the grand scheme of things, right? But the benefit is the length function massively simplifies in this case. So again, these problems are really all about where do you put that origin? Where do you set up your axes at to give you a convenient set of functions to work with? Right, so that's all I wanted to do. There wasn't really that much to do here. So I'll leave the video with this here, and have a good afternoon, everyone.